So, CSC, is it a good time to start?
Yes, sir, we can.
Okay, fine. Thank you. Yeah, so good evening to all of you. Hope that I am audible to all of you. Am I audible to all of you? Yeah, okay, fine. Yes, yeah, okay. I can say that, okay, welcome to IMT Ghaziabad, to all my students. And so this is the pre-foundation class, and I hope that okay, yeah, fine, I am audible. Okay. So this is the pre-foundation class, and as you know that today we are going to discuss something interesting means something new, I can say like that. Maybe some of you have heard this term Six Sigma, but today we are going to discuss some basic concept of Six Sigma and why we call Six Sigma as a process improvement technique or business process improvement technique. So I'm going to share my PPT. Before that, let me introduce myself. My name is Kaustav. I joined at IMT Ghaziabad in 2021. Before that, I was in ICFI IBS Hyderabad, ICFI Business School Hyderabad. I have a teaching experience of more than 6 years. And my main PhD domain is in supply chain management or in operations management. So I think this particular interaction, I think you will enjoy this interaction, and we'll see that how we can that the whole concept of Six Sigma is very interesting, and I'm sure that you will enjoy this entire session. So let's start with the presentation. Kindly tell me whether my PPT is visible to you or not. Is it visible? Hello.
Recording in progress.
Let me check whether my PPT. Okay, it's fine. Thank you. So now before we move into the discussion of Six Sigma, I'm going to give you 3 examples, and we'll try to understand those. I think we'll try to understand that why we need to study Six Sigma. Okay, so the first example is related to a software industry. I have mentioned the problem statement in my PPTs, and I think you can easily read those. I think the particular problem statement. So the problem is like that. There's a Indian software industry, and the end user of the software application, they raise a ticket whenever they face some sort of technical glitch or technical issues. Okay, so that's why that means it is mentioned the second line. That means the end user of the software application will raise the technical issues encountered while using the application as a ticket. Now, the client sorry, Pratik. Could you please mute yourself? So the client, they compile all those tickets at the end of the day, and then they outsource those issues, those technical issues, to the outsource partner in India. Now, the main thing is that company, they will try to resolve those technical issues with 40%. That means the service time, it is beyond 12 hours, which is, I think, as per the service level agreement, we have to complete this task within 12 hours. So that means, if I'm trying to find out that this 40% is a defect, that means as per the service level agreement, if I'm not able to complete, or if I'm not able to finish the job within 12 hours, that means the customer are not happy.
Client will compile the tickets.
Just a request from my side, please mute yourself. Okay. Now we move to the second example. In the second example is related to a manufacturing domain. So there is a bicycle manufacturing unit near Sonipat in Haryana, and their main product is that they are trying to manufacture the bicycle chain. And in the bicycle chain, this bush is the main component. Now, as per the customer requirement, that diameter of that particular bush, it will be within this range, which is 5.23 to 5.27 millimeter. So this is the customer requirement. They have mentioned this thing to the manufacturer. That means whenever you are going to manufacture the bush, the diameter of the bush, it should be within this particular range. And if the diameter of the bush, if it is go beyond this range, then we'll consider this as a defective item. So the acceptable range is 5.23 to 5.27 millimeter. Now, what we have identified here, that means this manufacturing process, if we consider the output, in the output, the rejection rate is very high. And the rejection rate is almost 8%. That means for every 100 product, there are 8 products which we consider as a defective item because their diameter is above that particular range. That means, so if I'm a manufacturer, so what I'm trying to do, so my main objective will be, I'm trying to reduce that particular, I'm trying to reduce the number of defective item. I'm trying to reduce my defect rate. Okay, so in the previous example, you have noticed that in the previous example, there is certain percentage, I think almost 40% of times we have exceed the service level agreement. In this current example, we have noticed that almost 8% of my product are defective. And now we'll move to our third example. In the third example, again, it is related to a service from the service sector. I have considered this particular example. So again, if you have noticed here, so this example is related to a US-based healthcare firm, and where they have a back office in India, outsource center at India. Now, almost there are 1,200 full-time employees who are working there in this center at India. Now, the main purpose, the main job is in terms of data entry, their payments, their claims adjudications, call center operations. All those are the main job that they need to perform. Now, what we have identified from this example, that in a year, almost these 312,000 claims annually they process. Okay, and based on that particular, and based on that, they will make the subsequent payments. Now, what we have identified that annually that this particular error, that means annually, I think almost 5,000. The exact figure is 4,898 number of errors we have occurred in the last one year. And they have also identified that means 1.5 claims are incorrect out of every 100 claims. And this further, it is noticed that 979 claims have incurred overpayment. That means that means this leads to a huge loss to the company. So if you notice all these 3 examples, the first example, the second one, and this current one, what will be your general conclusion? Anyone? In each of these 3 examples, the first example is related to a service level agreement where we are not able to perform. There are some cases where we are not able to perform or to meet that number of hours. The second example, that is the diameter of that particular product. As for the customer requirement, sometimes we are not able to fulfill that particular requirement. And in the third example, what we have noticed that there are some cases which actually that means almost 4,898 number of errors occurred in the last 1 year, and there are some I think overpayment kind of things are there. So what will be the general conclusion? I think if I'm trying to draw some conclusion based on these three examples, what will be your answer? Yeah, I can see that. Okay. Yeah, that means that the common thing is the main thing is like that. That means in each of these three examples, we are discussing about some process. Do you agree with me? We are discussing about some process. And what happened if we consider the output of the process, the output of this process, they are not accurate, they are not precise. That means there are some sort of variation. Am I right? There are some sort of variation. And due to this variation, what will happen? We see that sometimes our service level agreement exceed 12 hours, our diameter exceed the acceptable range, and there is some error in terms of the claim processing. Clear? So now how we can manage this process variation? How we can reduce the variability of my process? Because if we are not able to reduce the variability of my process, then obviously we'll generate more number of defective product. We'll obviously we're not able to fulfill that particular service level agreement of 12 hours, or maybe we'll process more number of error if we consider the third example. Am I right? Okay. So now the question is that what do you mean by the variability of a process? Obviously, that means now the next question that comes in your mind, that is, what is variability? Or what do we mean by the variability of a process? Am I right? I think you can unmute yourself if you want to speak.
Different results for a specification.
Yeah. So now in this slide, there are two diagrams. Okay. Now, suppose any of I have mentioned here two names, Arko and Aniket. So they are playing, suppose a rifle shot, or maybe they play basketball, or maybe they're playing golf. So now, if you see that their performance, I have mapped their performance in these two diagrams as a better quality.
But sir, so basically that means that there are some inefficiencies in his design, but he is very consistent in his process, in his application. Though sir, he's far from the target, but he's very consistent with what he's doing. So there might be issues with the design.
May I know your name?
So Vanshaj.
Banshaj, okay. Banshaj, now suppose if, as per, I think according to you, Aniket is a better player.
No,
okay.
No, sir. So both have their things. So Arko has hit the bullseye once. So his design might be correct.
Yes,
but his
absolutely right, Banshaj. That means I have mentioned two terms. If you remember, just few minutes ago, I have mentioned accuracy and the precision.
Yes, sir.
So in case of Arko, if you notice his performance, if you observe his performance, that means he's
Arko is more
accurate.
precise.
No, sorry.
No, Arko
is accurate
better
because,
precision, or in
because
better
sometimes
accuracy.
he hits the bullseye. But if I'm talking with respect to precision, that is missing in case of Arko. Whereas for Aniket, the accuracy is missing. Am I right? For Aniket,
Yes, sir.
the accuracy is missing. But if I'm talking with respect to precision, you can see that there is less variation. Am I right or wrong?
Yes, sir.
Yes?
Yes, sir.
So now,
Yes,
I'm just going to take. I think this whiteboard, is it visible to all of you? I'm writing here Six Sigma.
Yes.
Let me. I hope it is visible. Though my handwriting is not that much good, but still I think you can read it out. Okay. So in the first one, if this is that particular board, I think we are playing that, and this is the bullseye, and every time suppose I'm going to hit in this zone. Okay. So that means I can say that we are not, I think we are missing the target. Now, if I'm going to compare this particular diagram with my second example, in the second example, I have to manufacture the product within this range, 5.23 to 5.27 millimeter. Okay, so let's assume that my average is 5.25 millimeter. So this is my average or the standard mean, and then there is plus minus some sort of tolerance limit. Okay, that means if my objective is to develop or to manufacture the product whose diameter will be 5.25 millimeter, and if this is the output of my process, then I am not able to fulfill my customer requirement. Do you agree with me?
yes, sir.
Yes? Okay. Now, if I go with the second, suppose this is my second diagram, which is the bullseye, and maybe sometime I'm able to I'm able to hit the bullseye. But if you see the second one, let me give numbers. This is 1, this is 2. Now in the second one, you can say that I'm able to meet the target, which is 5.25. Sometimes I'm suppose I manufacture the product, and we notice that the diameter is 5.25 millimeter. But I can say that the process which I have developed to manufacture this particular product, every time when I'm going to manufacture the product, every time it will produce the product with a diameter of 5.25 millimeter. So this particular statement I can't make with respect to the second diagram. Is it clear?
Yes, sir.
Yeah, that means what we want. We want actually this third diagram we actually want. So we want that every time we can produce the product, or every time when we are going to offer the service, our quality or our variability is as much, I am trying to make it as less as possible. The variability of the particular process, I'm trying to bring it down, and I should be accurate and I should be precise, so that every time when I'm going to deliver the product or when I'm going to deliver the service, I must fulfill my customer requirement. That should be my main objective or main goal. Fine?
Yes.
Yeah, Ayush, you are absolutely right. Both precision and accuracy is essential. That means if I'm going to compare these three diagram, so obviously that means this particular process gives me the better quality product, or this particular process gives me the better quality service. Right? Clear?
Yes, sir.
Yeah. So the question is that how can I manage my process, or how can I reduce the variability of my process? So take the method which we are going to consider in order to reduce the process variability, in order to make the process more streamlined, or in order to reduce the defect rate. The technique or the method which we are going to consider, that is known as the Six Sigma process, where sigma, it stands for the process variability. Clear? Fine? Okay. Now, the question is that when we are talking, I think when we are going to discuss about Six Sigma, so first we have to discuss about quality. The question is, what is quality? Now, in the previous slide, if you notice, if this is the performance of this process, so I can say that both of these process can gives us the perfect quality or the quality as per the customer requirement. So when we're trying to define the quality, it is very much subjective because it varies to customer. Some customer wants consistency, some customer wants that means fast delivery, some customer wants that there is a usable product. Usable means that means it's providing a good with a use. I think in terms of the functionality, it performs well. So this, how we can define customer? There was a study conducted in US where they consider almost 86 different organizations just to understand what is the meaning of quality, or what are the different aspects that we can consider under the quality. So from this particular study, we have identified this set of aspects which we can use to define the quality. This in terms of the perfection, in terms of the consistency, elimination of waste, providing a good and usable product. That means it will fulfill your purpose. Doing it right for the very first time. Now, doing it right for the very first time, it complements the elimination of the waste. If you are a manufacturer or if you're a service provider, if you produce the product or if you deliver the service, and if the product or the service is fulfilling the customer requirement in the very first time, then you don't need to rework. And that means we can eliminate the waste, we can eliminate the cost, we can reduce our cost. Okay. So these are the several ways to define the quality. Now, the concept of Six Sigma, it actually, if I'm going to discuss the history of Six Sigma, actually the entire process, it starts, I think, in the year 1941, before the industrialization, I think the year. Okay, so earlier, what we'll see that most of the time we will, I think this is the evolution of the Six Sigma. We start with the inspection. The inspection means here I am talking about the visual inspection. Then we move to SPC. The full form of SPC is statistical process control. I will explain this term. Then we move to the another concept which is known as design of experiment, which is the extension of statistical process control. Then we move to the Taguchi's design. Taguchi is a very well-known researcher in the era in the quality domain. So Taguchi proposed a robust design, which we'll explain. I think once we finish this particular slide, then I will explain each of these terms. And after Taguchi, then we'll move to the quality management system, and this quality management system from there will enter into the era of Six Sigma. So now if I'm talking about this inspection, this visual inspection means that in that case, I think if you know that before this, I think maybe in the 1890s or maybe in 1900s, so in this particular year, so mostly we are producing a product generally one of a kind, and the volume is very less. Okay, so in that case, the quality assurance is mainly by inspection, the visual inspection. Now, after industrialization, so you can see, I think you can remember that there is a huge increase in the volume, which we call as a mass production. And once we entered into the era of mass production, where volume, I think, in terms of the volume is very, very high. Okay, so in that case, Now, the visual inspection is not possible. So then how do we ensure the quality? Because it is not possible to check each and individual product. In that case, so that means we need to, I think we need to assure that this particular quality is produced as per the customer requirement. So how do we ensure this thing? So then there are two researchers. I think their name is Walter Shewhart, and the second one is Deming. So they develop a new concept, a new method based on which we can ensure the quality of the product. And the main fundamental, the most thing, the main concept of this particular quality insurance is like that. That means if we focus on the process, if we monitor the process, or if we control our process, then it leads to, or it gives the better quality product. That means, so from after that industrialization age, or I think that particular time, we now focusing on the process, and that's why we name this particular method as statistical process control, or SPC. Now, this is a very, very interesting topic. That means we apply some statistical technique just to ensure the quality of the product or the service. Now, suppose this is the process. Just a second. Yeah. Now, this is the process. So, suppose we have this input, and these A, B, and C. So these are the three factors which we can control. Okay, suppose just take a very, very simple example. Suppose this process is a cutting process. And in the cutting process, we are going to cut a steel rod. Okay, so the input is the steel rod. And suppose these three factors are that speed, the angle, and the feed. So we can actually control these three factors, and at the end we'll get the suppose if I want a 5 millimeter diameter steel rod, so at the output we'll get that particular product, 5 millimeter steel rod. Now, how do I ensure that the process which we have developed, it will give me the exact product or exact diameter product? What we will do now, it is not possible to go and check individual product. What we will do, we'll take a sample. We took a sample, and suppose, and then we'll take the average. Suppose if the example is related to the diameter of the steel rod, so that means every time I took a sample of size, suppose 10 or 15 like that, and then I take the sample mean. And based on this sample mean, if we plot those sample mean, we'll get this normal distribution curve. I think I hope that all of you have heard the name of the central limit theorem. Do you know what is central limit theorem?
No, sir.
Okay, the central limit theorem says that if you choose the sample, if you increase the sample size, and if you then try to plot or try to find out the distribution of the sample mean, it gives you a normal distribution. Okay, so now, so once we plot this normal distribution, now what we will see that now in the normal distribution, before we move to the normal distribution, I would like to explain two terms, which is this LSL and USL. So these two are very, very important. This USL, it actually stands for upper specification limit, and this LSL, it stands for the lower specification limit. Now, this USL and LSL, I think the customer, they provide those parameters. If you remember the second example, as I mentioned, that suppose the diameter of the product which we are trying to, I think it is 5.25 millimeter plus minus 0.02. That is the tolerance limit. So this is the mean that we are targeting, and due to the inherent variation of the process, we kept this particular tolerance limit. So that means based on this, we can easily identify the acceptable range. Sorry. So 5.27 to 5.23, this is the acceptable range. That means if I'm able to produce the product within this acceptable range, the customer, they will happily accept my product. So now, based on this example, my USL is 5.27. That means the mean value plus the tolerance, and the LSL is 5.23, which is mean value minus the tolerance value. Clear? So this USL and LSL, that the customer, they will provide those information to us. So we know that I have to produce the product within this particular range. So now, that's why I have drawn these two straight line, USL and LSL. Now what you have identified, if this is the process output, this is the, I think we mapped the process output, we got a normal distribution. Now what we have identified, that there are some range of this normal distribution curve which is actually outside of this acceptable range. Do you agree with me? If you see the diagram, you can notice that with only this particular range, it is acceptable because the product within this range, they are within the range. I think the product between these two limit, they are acceptable because the quality of the diameter is 5.25 plus minus 0.02 millimeter. Whereas the product in this particular area, they are not acceptable. Why? Because the diameter is not within this range. The diameter is, maybe it is more than 5.27 millimeter. In this case, in this area, the diameter is less than 5.23 millimeter, which is not acceptable to the customer. So what we'll say, that means this, the product within this range, they will consider as a defective item. Am I right?
Yes, sir.
Yes, sir.
Yeah. Now the thing is that in statistical process control, apart from this USL and LSL, there are two more terminology which we need to define just to ensure that the process which we have designed will capable to fulfill the customer requirement. So those two terminologies are, one is known as UCL. The UCL, it stands for upper control limit, and second one is LCL, which is stands for lower control limit. Fine. Now this UCL and LCL, these are the two imaginary line which we consider just because to ensure my process is capable enough to fulfill the customer requirement. And we assume one more thing. We assume that this upper control limit and the lower control limit, they are plus minus 3 sigma distance away from the mean position. That means, just give me a second, I want to open my whiteboard. So suppose this is the process mean. This is the distribution which we got after plotting all those sample mean. Now this is my USL and this is my LSL. So these are my acceptable range. These are the defective item range. Okay. Now what we'll consider, that we have defined these two terms, UCL and LCL. So these UCL and LCL, they are plus minus 3 sigma distance away from this process mean. That means from this side 3 sigma, from this side 3 sigma will define UCL and LCL. Now for the time being, if we consider, just I hope it is visible to you. So this is my USL, which is as same as UCL, and this is my LSL, which is equal to LCL. Now it means what? It means what? Can anyone tell me what is the meaning? I think can you draw some sort of inference from this diagram?
LSL is 3 sigma and USL is 3 sigma away from
Absolutely.
me.
That means if we consider my upper specification limit is equal to the upper control limit, and my LSL is also equal to the lower control limit, it means that my upper specification limit as well as the lower one, they are plus minus 3 sigma distance away from the process mean. So if my process mean is 5.25, that means, so this one will be how much? 5.25? Sorry.
Plus
5.25.
3 sigma.
Minus 3 sigma.
Plus
Plus minus
Oh,
3
my
sigma by 2.
that is
Oh, okay.
USL, am I right?
Yes,
Yeah.
sir. Yes, sir.
Minus 3 sigma, that is LSL. Clear?
Yes, sir.
Am I right? Okay. Now, under this condition, can any one of you tell me, if suppose I am going to produce 1 million product? Okay. So, can anyone tell me that how many defective item we are going to produce if we produce this much of product? From this process, how many defective item we can generate if we produce 1 million product? Any idea? Or is it possible to calculate? First tell me. Is it possible to
First of
calculate?
all, we don't know the rejection rate, no, sir.
Mhm.
We don't know the rejection rate, so how could we get the data?
Okay. Okay. What's your name? Sorry.
Shankaram, sir.
Shankaram. Okay. Any other answer? He has mentioned that we don't know the rejection rate, so that means it is not possible to calculate. Any other answer? Is it possible to calculate the number of defective item?
0.2, sir.
0.2. Okay. Okay. Fine. I think without wasting time.
Using the probability distribution curve and Z, it
Absolutely.
is possible to
Absolutely.
calculate.
Anand. I think Anand is your name. Yeah.
Yes, it's Apurva
So,
Anand. Yes, sir.
I think now there's a, now for normal distribution, I think there is a basic concept. I think all of us, I think we know, if this is the normal distribution, the bell-shaped curve, which is symmetric in nature, and this is my process mean. So this is the mean. I think it has some characteristics. From the mean, if we move 1 sigma from this side, it is minus 1 sigma. That means we are covering this much area.
Yes, sir.
From the process mean, if we move plus minus 1 sigma, that means this much area we are covering.
Yes, sir.
So can you please tell me what is the
95%.
90, I think 95.4. And
Excuse
if
me,
we
sir.
move, yeah,
So how could you please explain how it is 68%?
this is
and
a
how it
standard,
getting
this
this
is
value?
standard characteristics of the normal distribution curve.
Okay, thank you, sir.
This is the standard. I think we can prove mathematically, but this is the standard characteristics of the normal distribution curve. Okay. And if we move to plus minus 3 sigma from the process mean, that means this is the plus minus 3 sigma. Let me draw. This is plus 3 sigma. This is minus 3 sigma. That means we are actually covering
99.9.
99.9.
0.73%. Okay. So based on these standard characteristics of the normal distribution, now if I come back to this particular problem, that means I know that my USL is now plus 3 sigma distance away from the process mean. My LSL is also minus 3 sigma distance away from the process mean. So I think this is my total area within plus minus 3 sigma range. Okay. And the product within this area, they are acceptable. Do you agree with me?
Sir,
Yes.
I understand how did we arrive at 3 sigma plus minus 3 sigma? How did we arrive at that?
Lower control limit, they are plus minus 3 sigma distance away from my process mean. And if the upper specification limit is equal to the upper control limit, then I can say that my upper specification limit is also 3 sigma distance away from the process mean. Similarly, the same
Yes,
thing will
sir.
happen to my lower specification limit, LSL.
Yes, sir.
Okay, that means
Yes, sir.
my USL and LSL, they are both 3 sigma distance away from my process mean.
All right, sir. Sir, and
Yeah.
essentially, are specification limits and control limits the same, or can they be different?
No. Ideally, what we are trying to do, because if we consider these two things as similar or same value, USL and the upper control limit, so there is a high chance that maybe we can generate more number of error. I will show you. Okay, now since you are asking this question, then I will going to draw this. This is the upper specification limit given by my customer. This is the LSL. Okay. Now what we'll do, if I'm trying to bring the process, and for the process, this is my upper control limit and the lower control limit. That means this is my process. That means I'm 100% sure that I can, whatever the product I'm going to produce, it will always within the range. That means the number of error in this case is very, very less than the previous one.
Okay, so sir, at least theoretically, you can say that there is no scope of error in this one.
Absolutely. That means, and that main theme of Six Sigma, we are trying to reduce the process variability. Now, if you see that in this diagram, and if you are going to compare this diagram with this one, so what you can notice, so the variability of the process is reduced. What do you mean by variability? The spread?
Yes, sir.
So in this diagram, if you see that the spread is much higher than this case.
Correct, sir.
So that means the probability of generating more defective item in this situation is higher than this case.
Yes, sir.
Clear? So ideally, we are trying to design the process in such a way so that I can reduce its variability.
Right, sir. Thank you, sir.
Okay.
Sir, but have we defined sigma already? Like, what is sigma here? We are saying 1 sigma, 2 sigma, 3.
Sigma, we are not defining yet here. Sigma,
okay.
There's some process to calculate the sigma, but I'm just going to give you the concept.
So, sir, without knowing sigma, it is not making much sense. Like, oh, okay, sir. Okay, now it makes sense.
Okay. So this mistake is from my side. I forgot to mention what is sigma. Sigma is the, I'm just going to write it here. Sigma is the standard deviation of the process.
Okay, sir. Thank you, sir.
Okay, fine. Now come back to this example. So now can you tell me that what is the number of defective item that we can generate if I'm going to produce 1 million product from this diagram?
3,000.
That means for plus minus 3 sigma, that means my acceptable range is plus minus 3 sigma, this area. And this area, it covers actually 99.73%. Am I right? This entire area, it is 99.73. Hello?
Yes, sir.
Yeah,
Yes, sir.
that means So what is that means this particular area thing which is outside my USL and LSL. So this is how much? This is 0.27%. This is 0.27%. That means
Yes.
out of 1 million product, if we follow this particular process, so this process will produce almost 2,700 defective product out of a million product from this particular process. Do you agree?
Yes, sir.
That means the number of defective item is, I think, is quite high. So what we'll do, if we reduce the variability, if we squeeze the process, if that means if I'm trying to make this particular process, then I can say that out of 1 million product, maybe the number of defect will be very less. Maybe I think we can produce 1 million quality product if we follow this particular process. That means if we can reduce the variability. Clear? I hope it is clear.
Yes, sir.
Yeah.
Equate that range
We are
between
trying
LSL and
to
USL.
make that
So-
range less than USL and LSL.
Okay.
If you see these two diagram, so in this case, what we did, we make this thing equal. We make USL is equal to the upper control limit. We make LSL is equal to the lower control limit. And what happened at the end, we are going to produce 2,700. We are going to produce 2,700 defective product out of 1 million. Okay.
So, sir, in this figure, sir, when UCL is equal to USL and LCL is equal to LSL, then the defect rate is 0.27%. So basically, our objective is to make the range of the control limit smaller than the
Absolutely.
range of the specified limits. If customer has, let's say, allowed a range of 1 centimeter variability, so our target should be to reduce it to 0.8, even better than what the customer wants, so that we keep on
Absolutely.
reducing the defect.
That means, yeah, so that it is just a safeguard.
Okay.
It's
Any,
just a safeguard.
Sir, towards noise, sir, as it was mentioned below that noise is beyond our control.
Noise,
So basically-
though I mentioned noise is actually those sort of factor which we can't control. Okay, what happens? Suppose there is the machine is working, there is sudden breakdown in the machine. Okay, and due to that breakdown, so maybe the diameter of the product is goes beyond the that particular range. Or maybe the operator who is working there, maybe he or she is, I think that person don't have that adequate knowledge or training, so that's why he or she is not able to perform, and it leads to a generating a defective product.
Thank you, sir. And sir, just one more small thing, sir. Sir, sigma is the standard deviation. That basically how the members of a group differ from the mean. It is basically defined like that. So, sir, what's the fundamental difference sigma and and three sigma, sir? Might be very basic.
Okay.
Might be a very basic question.
I got your question. Can you please give me 5 more minutes? I can explain to you within a diagram. Okay.
Thank you.
Okay, so this is the fundamental concept of SPC, statistical process control. Now then we'll move to the next category of I think quality enhancement, you can say like that, which is the design of experiment. Now design of experiment, what actually happened? Now if you see this particular diagram, now so there are three factor A, B and C which I can control. Okay, now if I want to redefine my process, or if I'm going to tune those parameters to get the product within the within this particular range, within USL and LSL. Now, which factor out of ABC we can consider? Because it is not possible to go and check each of these factor. That means I can't check A separately, B and C, because it is the kind of experiment, and to perform this sort of experiment, I think it will actually there's a huge cost are involved in this kind of experiment. So how can I decide that out of these three factors, which factor should I consider, or which factor, if I'm going to tune down, will give me the perfect product or will give me the quality product? So that particular things we can identify based on this design of experiment. And this design of experiment, and Taguchi actually he developed this particular concept, DOE, and based on this DOE, he actually developed another concept which is known as the robust design. And I'm not going to give in details of this Taguchi's design or DOE. Now, after that, now we know how to manage this process. We know how to manage our process variability, but there is something missing in terms of that. We have people, we have machines, we have process, we have material, but the management term is missing. We need a proper management, and that's why they have developed the quality management system. And under the quality management system, one of the most famous concept is TQM, Total Quality Management, which is a continuous improvement process. Based on this particular method, how we can improve our process, how we can reduce the variability of my process, or how we can ensure the quality of my process in a continuous improvement manner. That is the of TQM. I think measure the performance of TQM. Okay, so what they did, I think those researchers now they are trying to identify the real impact of this quality assurance profit, and that's why they have developed this particular concept of Six Sigma. So when Six Sigma means they are trying to reduce the process variation, they are trying to reduce the defects, and actually you can see that it will make an impact on your bottom line. So that visibility is I think that particular impact is quite visible in case of Six Sigma. That means by using Six Sigma, you can easily increase your profit level. So in case of Six Sigma, the standard term is when we mention the term Six Sigma, it means that in Six Sigma, if we are trying to reduce the process variability, we can end up of producing less number of defective product. And in case of Six Sigma, our goal is that we are not going to produce 3.4 more than 3.4 defects per million. This 3.4 ppm, it stands for 3.4 number of defects per million. In the earlier case, we produce 2,700 defective product. And if we follow the Six Sigma approach, Six Sigma means this concept, but it has a method, it has a systematic method which we need to implement. And based on this systematic method, if we follow the particular method, we can end up of reducing the number of defective item, which is 3.4 million 3.4 defects per million. So I think this it was pioneered by Motorola in 1980s. Mr. Bill Smith, who developed this particular concept of Six Sigma, and then it was popularized by Jack Welch, General Electric, who actually make this thing popular in the whole world. Now, I think we have discussed this thing. Let me show you this diagram. Now, I think this diagram is visible to all of you. It actually helped me to explain that why Six Sigma is better, or what the meaning of Sigma here.
Yes, sir.
Okay. Now I request you first observe this first diagram. In the first diagram, have you noticed anything?
Sir, the second diagram is more sharp, like it has a more sharper peak,
No.
whereas the first diagram is little
Just first
broad.
focus on the first diagram. This first diagram is actually, that means my upper control limit and the lower control limit, they are equal to USL and LSL. So here we represent S, just S is used to represent the standard deviation or the process variability. So you can notice that so this dotted line represent my upper control limit, which is equal to USL. This dotted line represent lower control limit, which is equal to LSL. Okay, so that means my upper control limit and the lower control limit, they are plus minus 3s distance away from my process mean. So this is this central line, it represents the process mean. So I think we have already explained this example. That means the first diagram, or based on this first process, this is the number of defective item that we can generate if we follow this particular process. Clear? Now what we will do, now we are trying to reduce the process variability by applying the Six Sigma concept. We are trying to reduce this S. Now, after applying the Six Sigma concept, we got a variability S cap. So between the central line, between the process mean and between the upper control, between the lower LSL, lower specification limit, between this range, now we can accommodate 6 S hat. Earlier we can accommodate only 3s, which is my process variability in the first diagram. Whereas in the second diagram, we reduce the process variability by applying the Six Sigma concept. Now we can accommodate 6 standard deviation between my central line or between my mean value and upper or lower specification limit. Okay? Is it clear or not? Hello?
Yes, sir, but how it could be helpful to us?
No.
How the data will be helpful?
No. This I think that this concept actually, this is my Six Sigma concept, because Six Sigma means that we can reduce the process variability in such a way so that we can accommodate the 6 standard deviation between my upper control limit and upper specification limit. Sorry, between my mean and USL and between my mean and LSL. So this 6 from this side and this 6 from this side, that actually the statistical representation of the Six Sigma.
So that is overall 12 sigma difference we have in between.
Absolutely. So there's a common mistake I have noticed in several times, that students consider Six Sigma is this one, because they have considered 3 sigma plus 3 sigma, which makes 6 sigma. But that is a wrong concept. Six Sigma actually, that is the 6 standard deviation we can accommodate between process mean and USL and process mean and LSL.
So sir, basically this sigma and sigma cap is reverse. It's a reverse calculated, reverse engineered in this sense that this 3s is the variability allowed by the customer. So sir,
or in this case, that S is the variability. Okay. So
it is the variability of our manufacturing process.
Of the process.
Okay.
Manufacturing process. Okay. Now this USL and LSL, it is defined. Okay. Suppose that is, if we took the previous example, 5% 5.25 is the center and USL is 5.27 and LSL is 5.23. Fine. That means between 5.25, between the center line and USL, that means 5.27, we can accommodate the 3S. This S value is known to us. This S value we have calculated based on my process. So between this range, we can accommodate only 3S. That means my process variability is so high so that only we can manage 3As between the central line and USL, or maybe central line and LSL. Now my objective is I want to reduce this standard deviation of my process. I want to reduce this value of S. So I have applied some technique, which is the Six Sigma technique. And that actually helped me to reduce my process variability to S, suppose S cap. So this is the new process variability which we have identified after applying the Six Sigma concept. Now my USL and LSL still remain fixed. That is 5.25, 5.27 and 5.23. And we got a new value of the process variability. So with the help of this new value of the process variability between this range, between the gap of central line and the USL, now I can accommodate 6 value of this sigma cap.
So, sir,
Sir, in the previous
so, sir, basically,
means
our
I want-
target.
One by one, please go by one by one. Hello?
yes, sir.
So, sir, basically, our target is that, sir, let's say, sir, let's say the customer has allowed a variability of 6 millimeter on either side. So, sir, between the
Fine.
central line and this USL, let's say there are this allowed limit is 6 millimeter. So, sir, our target is to make our production process so, sir, precise and accurate that this variability is just 1/3 of it in the first case. And this second case that we want to improve our process to such an extent that this it is just 1/6 of the allowed limit by the customer.
Okay, I'm
Is that the right way to say?
going to tell you. So mathematics is easy. So suppose it is K into standard deviation. Standard deviation equal to tolerance by 2. So this K means whether we are want to achieve 3 sigma, 6 sigma, like that. Okay. So suppose in this process is a 3 sigma process. So where the K value is 3. Okay. And this is a sigma value. Now, as per this example, my tolerance limit is 0 to. From this example, what is my tolerance limit? 5.25 plus minus 0.02.
Yes, sir.
Okay. So this 0.02 by 2. So from there, if I want to manage a 3 sigma process, we can calculate the value of sigma there. What was the value of sigma? It's 0.02 by 6. Okay. Now, if I want to make it a 6 sigma, so the value of K will be now 6. And this is sigma into 0.02 by 2. So now if I want to make it 6 sigma, so what will be my sigma value?
0.01
by 12.
Okay. 0.1
That
by
means-
6.
So this,
Standard deviation is much less. It is just half.
so that's why if you observe these two diagram, so in the second diagram, my process, the variability is much less than the previous one.
Got it, sir. Thank you, sir. Thank you so much.
Clear? Now the question is that, okay, statistically we have understood, we got the concept, but as I mentioned, that Six Sigma is a structured method. There's a systematic method based on which we can able to reduce So DMAIC actually, DMAIC is the systematic based on which we can able to reduce the process variability. Now in this DMAIC, this D actually it stands for define. This M stands for measurement. This A stands for analyze. This I stands for improvement, and this C stands for control. So based on DMAIC method, DMAIC step or technique, we can reduce the standard deviation of my process. Now, apart from DMAIC, we'll explain this DMAIC in details in term 3. We have a course of Six Sigma where we are going to discuss in details of each of these 5 individual steps of DMAIC. What do you mean by define? What do you mean by measurement? What is analyze? What are the different kind of techniques that we can consider under the improvement process, and then control. So in details that we are going to discuss in our term 3. If you're interested to take operations as a major, then we'll going to discuss all those things. One more systematic process which we can consider in Six Sigma, it is known as DMADV. So one is DMAIC, the second one is DMADV. So again, in this case, DMADV, the first D it stands for define, M stands for measurement, A stands for analyze, and the second D, it actually stands for design. So this D stands for design, and it is verify. So the question is that when should we apply DMAIC and when should we apply DMADV? Now the thing is that we only apply DMAIC when there is an existing the process is already existed in our plant, or the product is already there in the market. If I want to improve the process, or if I want to improve the product which is already there, then in that case we can apply the DMAIC. And if we are trying to develop some new process or new product or new service, then we are going to apply this DMADV. So that is the difference between the DMAIC concept with the DMADV concept. So again, all those things we are going to discuss in details in our term 3 operations management. If you are interested to take operations management as your major, so in that term 3 we'll discuss each and everything of this particular Six Sigma concept. Okay, and I think I'm going to stop it here. I think already I have consumed 1 hour. So, and just few things I need to discuss with you. In IMT, as I've already mentioned, in term 3, we have this particular subject. Also, in the last 3 years, I think maybe you can notice this thing maybe in your brochure or maybe in our website. We have conducted some certification course from KPMG. I think there are 3 different certification course. The first one is the Green Belt, which I think all the students who are who will join at IMT, they are eligible for this Green Belt course. So this Green Belt is the basic certification course for Six Sigma. And after having this Green Belt, we are also conducting one more training program that is known as the Black Belt along with KPMG. So this Black Belt program, actually, it is only for the operations major student. I think once you will be in second year, then you can go for this particular training of Black Belt. And in the first year, you can actually do this Green Belt certification course along with KPMG. Okay, so that's all from my end. And now, if you have any query, or if you want to know anything, you can ask me.
Yes. Excuse me, so I had it out.
Yeah,
So,
please.
just
what could
before
be the
this session, I was
acceptancy rate?
expecting
So what could be the acceptancy rates for every sigma in a Six Sigma rules?
Sorry,
For 3 Sigma, you said what's the acceptancy for every sigma?
acceptancy. I think that the defection, that
Yeah.
defect rate I have mentioned, that is, we are trying to make it 3.4 defects per million, but it is too difficult. And actually, the Six Sigma process we apply just to bring down the defect rate from our existing value. Suppose if my current process is going to produce, suppose 3,000 defect in per million product, and we apply Six Sigma, or we apply this process improvement technique by applying, maybe we can go for DMAC or generally DMAC. And by applying DMAC, we are trying to bring it down. Maybe it's around 1,200, or maybe it's below 1,000. Okay, so that is nothing. From the current level, we are trying to reduce is as much as possible.
So, can I ask a question?
Yeah, please.
Yeah, so before the session started, I was expecting something more basic one with what
Please
we
give it
have done
louder.
today. Am I audible now, sir?
Yeah, you're audible.
Yeah, so I was saying I was expecting a little bit more basic than what we were taught today. So is this what you would define as the basic for the operations measures of what we learned today? Because there was a lot of prerequisites which would be needed to understand the things which were taught today. I was
I think because this particular topic, it will appear in the third semester. And I thought that you all of have some sort of the statistical experience, because we mainly deals with the normal distribution, and those concepts which I have explained in this current session, that is the very fundamental concept of normal distribution.
So there were very many values like we were talking before, the 68% of the graph or the 90% of the graph, or there was some information regarding the sigma and the 3 sigmas and the 6 sigmas. There were many students which were able to understand that. They were able to understand which different kind of acronyms exist in this operations tool. And I, as a fresher, I wasn't able to understand that.
This particular topic will come in the third semester. So before, I think you are term 2 and term 1, where we deal with the basic concept of operations management.
Okay, so is there anything apart from that? Are there any other prerequisites we should know apart from the studies which we will do in the end?
And this is not though Six Sigma, I think it starts from a manufacturing domain. So that means all of you think that it will relate to the operations, but you can see that this Six Sigma, this application of Six Sigma, I think in each and every sector, in finance, banking, marketing, in all sectors, you can find some sort of application of this Six Sigma.
Thank you, sir.
Yeah.
Sir, I want to ask one question. Sir, I am from PGDM marketing, but I want to opt operations as a minor. So how when we will be actually able to choose it as minor, sir?
I think after term 3, I think then you can able to choose your minor.
Okay, sir.
Anything?
And sir, when we have to choose our major?
I think when you are in term 2, so then you need to decide your major.
Sir, we saw that before we came to Six Sigma, there was a 3 Sigma process, right? So, sir, in principle, in theory, this can be reduced to as much as we want, right? If we have processes that are so robust,
theoretically it is possible.
So we can
when
have
you
a
go
Sigma process also.
It is possible, mathematically and theoretically is possible, but it is in terms of the implication of the execution. So because for each and every activity, though I mentioned only the DMAC process, so you can see in the DMAC, so from the defined stage, there are a lot of different activities that you need to perform. And for each and every activities, there are some sort of cost are involved. So
Yes.
the expenses will become quite high.
Okay, sir. Sir, so as of now, the most efficient process we have is Six Sigma only.
Yeah, till now it is Six Sigma.
Thank you.
Sir, I had a question.
Yeah,
Sir,
please,
this
question up.
so the Six Sigma, which the graph which we saw was for a manufacturing plant, but what will happen in case of service? Sir, will we still have the USL and LSL? Sir, in that case,
Absolutely, absolutely.
so what will be the parameters on
Suppose if you consider the first example, that is regarding a service level agreement, that means I need to fulfill the demand or not demand. I mean, if there is some technical problem, I need to help my client. I need to resolve those technical problems within 12 hours. Okay.
Yes, sir.
In
Yes,
the
sir.
first
Understood.
example. So
Yes, sir.
12 hour is my USL.
Okay. Okay. Yes, sir. Understood. Thank you, sir.
Yeah. Welcome. Any other doubt or any query?
Sir, in that case, the first one, so 12 hours is the USL. So what's the LSL, sir? Is
LSL,
it possible
is
that
it-
there is no LSL?
Not. I think theoretically 0 is the right answer.
Yes, sir. Yes, sir. Yes, sir. I was
But it
thinking
is
that.
not
just
possible
wanted to-
that to make it 0. So I think as less as possible. Less than 12 is the LSL. So USL is 12 and less than 12 is any value that you can consider for LSL.